Welcome everyone. Today we will look at some examples of Fourier transform and then later on look at how to obtain the Fourier transform of a periodic signal. We studied the Fourier transform expressions last time. The inverse Fourier transform is like this, where we use the spectrum or xj omega to reconstruct xt, and the Fourier transform itself is xj omega equals the integral from minus infinity to infinity xt e to the power of minus j omega t dt. So when we are given a time domain signal xt, to obtain the Fourier transform, we use this expression. Okay, let's take this as our first example. Find the Fourier transform of the signal xt equals e to the power of minus at ut, where a is greater than 0. So you can see, because of the presence of ut, this signal is non-zero only in the positive side of the time axis. So if you plot this, the signal looks like this, 0 from minus infinity to 0, and then at t equals 0, the signal is 1, and then it is an exponential decay. So we know that ut is like this, 1, and then if we plot e to the power of minus at with a greater than 0, the signal looks like this. So therefore when we multiply these two signals, this is what we obtain. So now we apply the Fourier transform analysis equation to obtain the Fourier transform of this signal xj omega equals integral from minus infinity to infinity xt to the power of minus j omega t dt. So when we substitute this particular xt, we can do the integration from 0 to infinity because of this nature of the signal, e to the power of at times e to the power of minus j omega t dt. So we can gather the terms. So the integral looks like this. E to the power of minus a plus j omega t dt. So therefore we get minus a plus j omega 1 over e to the power of minus a plus j omega t, and we must apply the limits 0 to infinity. So when you put infinity to this term, we know that a is greater than 0, so we have minus at times e to the power of minus j omega t. So you want to set limit t goes to infinity. So you can see this one has the magnitude 1 as we have seen before, and this one's magnitude becomes 0. So as a result, you have 1 over minus a plus j omega 0 minus 1, which is 1 over a plus j omega. Alright, so this is the answer. So you can see the Fourier transform is a complex number. So therefore when we plot this, we have to plot the magnitude and the phase of that. So the expression that we got is this, xj omega is equal to 1 over a plus j omega. Now we want to obtain the magnitude of this. So one way to obtain the magnitude of this is to have the magnitude of 1 divided by magnitude of a plus j omega, so which is 1 over a squared plus omega squared square root. So therefore you can see when omega is equal to 0, it's 1 over a. When omega is equal to a or minus a, it's the square root of 2a over 2. Also, we can obtain the magnitude if we like by multiplying the denominator and the numerator by the complex conjugate a minus j omega. So a plus j omega and a minus j omega. So then again you can obtain the magnitude of this. You get the same answer. So when you think about the angle, so since this is x j omega is actually equal to a minus j omega divided by a squared plus omega squared, the angle of x j omega is equal to a tan 2 minus omega comma a. So therefore you can see when omega is equal to minus infinity, it is plus pi by 2, and when omega is equal to infinity, it is minus pi by 2. So when omega is equal to 0, it's 0. So you can see we have plotted the magnitude plot and the phase plot of this signal, Fourier series, Fourier transform, I'm sorry. Okay, so as a next example, we will look at xt equals e to the power of minus a modulus of t. So when we look at the signal, you can see that if you plot this signal, so xt is equal to, when t is greater than 0, it is e to the power of minus at. When t is less than 0, it is e to the power of at, and we have been given that a is greater than 0. So therefore if you plot this, so signal would look like this. Okay, now we can apply the Fourier transform analysis equation. So instead of xt, we need to put this e to the power of minus a modulus of t e to the power of minus j omega t dt. So now we have to break this integral from minus infinity to 0. During that interval, it is e to the power of minus at, and from 0 to infinity, it is e to the power of minus at. So we do not go into details, but you can see that these are the expressions that you would get inspired by the previous example. So when you simplify these things, you get 2a divided by a squared plus omega squared. Now this is a real Fourier transform, so therefore we don't have to plot the phase. So this is the signal, and that's the Fourier transform. It turned out to be 2a divided by a squared plus omega squared. When omega is equal to 0, it's 2 over a. When omega is equal to minus a or plus a, it is 1 over a. Okay, so once again we observe that here xt is real and even. So our Fourier transform is also real and even. So we experience a similar phenomena for a periodic real and even signal like the cosine cos omega naught t, where we found out that our AKs were real and even. Okay, now let's take this example. Determine the Fourier transform of the unit impulse xt equals delta t. So this signal is actually this. It is an impulse of area 1 located at 0. So you know that this impulse does not have a finite height. Its area is 1. So we can apply the expression xj omega equals minus infinity to infinity xt e to the power of minus j omega t dt. So you know that if you multiply a signal by t minus delta t minus t naught, some signal like yt, for practical purposes, you can write this as yt naught. So similarly, you can replace this omega as t equals t naught 0. So therefore you get 1 as this integral. The unit impulse has a Fourier transform consisting of all equal contributions at all frequencies. So if you plot xj omega for this, you will have a 1 constant. Okay. So this is intuitive for us when the signal is infinitesimally short in time axis. It is infinitely wide in the frequency axis. Okay, now let's look at the rectangular pulse and obtain its Fourier transform. So this rectangular pulse is 1 when t is less than t1 and greater than minus t1, otherwise it is 0. So we can plot it like that, from minus t1 to t it is 1. Okay, let's obtain the Fourier transform of this. So xj omega equals minus infinity to infinity xt e to the power of minus j omega t dt. So we can do the integration by putting 1 when the signal is from minus t1 to t1. So when you do the integration, you will have e to the power of minus j omega t divided by minus j omega, limits are minus t1 to t1, and then when you have applied those limits, you will get e to the power of minus j omega t1 minus e to the power of j omega t1 divided by minus j omega. So we know Euler's relation for sine theta. Sine theta is e to the power of j theta minus e to the power of minus j theta divided by 2j. From this relation, we are able to obtain that this is equal to 2 sine omega t1 divided by omega. Okay. So when you plot this, this is the form that you get. You can see it's a sinusoid divided by omega. So when omega is actually equal to 0, you have to apply use the L'Hopital rule to obtain the limit. So let's try that. So limit omega goes to 0, 2 sine omega t1 divided by omega, so which is equal to limit omega goes to 0, the derivative of sine 2 t1 cos omega t1 divided by 1. So you put 0 here, so it is 1. So you can see you get 2 t1 right here. Okay, so since this is a sinusoid, you see that when omega is equal to minus pi divided by t1 and pi divided by t1 and so on, you get when omega t1 is multiple of pi, you get zeros. Okay, so this is a very nice shape. This has a special name called sinc. We will look at that concept later. Okay, now let's consider the signal xt whose Fourier transform is this one. So 1 from minus w to w, Fourier transform. So we have to determine xt. So we have been given the Fourier transform, we have to determine xt. So it is quite the same as obtaining the Fourier transform, obtaining the inverse Fourier transform. So we use the synthesis equation or the inverse Fourier transform, 1 over 2 pi minus infinity to infinity x j omega e to the power of plus j omega t dt. So what is the formula for x j omega? It is minus infinity to infinity xt e to the power of minus j omega t dt. Alright, so we can do this computation from minus w to w it is 1. So when you carry out this integration, you get sine wt divided by pi t. Okay, so you can see that also has that special shape of a sinc. Here you can see some duality now, similarity between the time and frequency domains. So what we saw was, when you take a pulse in time axis, its Fourier transform turned out to be the sinc shape. So if you take Fourier transform a rectangular pulse as a Fourier transform, the time domain signal, this one, turns out to be of the sinc shape. So we will look at this duality later on. Okay, so now let's introduce the sinc function. Our definition is sinc theta is equal to sine pi theta divided by pi theta. Some people have a different definition, but remember, in our case, sine pi theta divided by pi theta. You can see this is the plot of this signal. So once again, by applying L'Hopital rule, you get its magnitude here is 1, and then whenever theta is an integer, you get zeros. Okay. All right, now let's express these two signals using this definition. So sinc theta is equal to sine pi theta divided by pi theta. So sinc theta is equal to sine pi theta divided by pi theta. So we have to make this angle look like pi theta. So let's take this. So this is 2 sine pi omega t1 divided by pi. Okay, so we have to write a similar form here. So 1 over t1 pi omega t1 divided by pi. Okay, therefore you get sinc omega t1 divided by pi and 2t1. This expression. So for the other one, I will directly write the answer. You can verify on your own. All right. So what happens as W increases? As W increases, xg omega becomes broader. So let's take the relationship once again. Write it down briefly. So this is the relationship that we got. So here is our pulse, and we got xt for this as sine wt divided by pi t. So sine wt divided by pi t, and that is our xt, and our xj omega was given as this. Okay, so as W increases, you can see the Fourier transform widens, becomes broader, while the main peak of xt at t equals 0 becomes higher, and the width of the first lobe of this signal, that is a part of the signal for t less than pi over w, becomes narrow, because we saw that when you plotted this, it is from minus pi by w to pi by w, the width of the main lobe, and the height also w divided by pi. So as w increases, height increases and the width decreases. In fact, in the limit as w goes to infinity, xg omega becomes 1 for all omega, and consequently we see that xt converges to an impulse as w goes to infinity. Now the behavior is an example of inverse relationship that exists between the time and frequency domains. Alright, pictorially, so you can see In this case, this is x1 j omega, the Fourier transform, the frequency spectrum in omega axis. So w1 to w1, it is wide. So because it is wide in a time domain, x1t is narrower and the height is higher. So when we shorten this, this becomes broader and height becomes lower. If we shorten this further, the height becomes lower and the pulse becomes lower. Okay, now let's look at the Fourier transform of periodic signals. But we already know that for periodic signals, it is a Fourier series that we compute. That means AKs. That means our frequencies are harmonics of omega naught, the fundamental frequency. In the previous section, we studied the Fourier transform representation station, paying attention to aperiodic signals. We can also develop Fourier transform representations for periodic signals. This allows us to consider periodic and aperiodic signals in a unified context. We can construct the Fourier transform of a periodic signal directly from its Fourier series representation. That means using AKs. Consider signal xt with Fourier transform xj omega. There is a single impulse of area 2 pi at omega equals omega 1. So let's consider an impulse at omega equals omega naught right here, and we call its area as 2 pi. It's not the height, it's the area, remember. Alright, so that is our Fourier transform. Okay, so let's determine the signal xt. To determine the signal xt, we apply the inverse Fourier transform expression. Xt equals 1 over 2 pi from minus infinity to infinity xj omega e to the power of j omega t d omega. So there you go, 2 pi omega delta omega minus omega naught. So we can substitute this omega with omega naught minus omega naught, and then plus omega naught. Then that would be the answer, because this is a constant with respect to omega. So you can see for an impulse of height 2 pi located at omega naught in the frequency domain, the corresponding time domain signal xt is this complex exponential. So more generally, if xt omega is the form of a linear combination of impulses equally spaced in frequency, that is, now let's not consider just one pulse delta omega minus omega naught, but let's consider many of them. Delta omega minus 2 omega naught, delta omega plus omega naught, delta omega plus 2 omega naught, and so on. Let's consider all these things multiplied by AKs. And so on. This one. And also multiplied by 2 pi. For this, xt would be exactly the summation of all these complex exponentials multiplied by ak from this relationship that we have here. So which is exactly the Fourier series representation of a periodic signal. Thus the Fourier transform of a periodic signal with Fourier series coefficients ak can be interpreted as a train of impulses occurring at harmonically related frequencies, and of which the area of the impulse at the kth harmonic frequency k omega naught is 2 pi times the kth Fourier series coefficient ak. So how do you, if you know AKs, the Fourier series of a periodic signal, how do we obtain the Fourier transform? We multiply AK by 2 pi and locate impulses at k omega naught positions in frequency. Okay. Okay, let's take this example. Find the Fourier transform of the square wave signal whose Fourier series coefficients are these, and this is an expression that you obtained before for the square wave signal, the sine k omega naught t1 divided by pi k. Alright, we know the AKs. So how do we obtain the Fourier transform? We multiply the AKs by 2 pi and locate impulses at omega at k omega naught. So it's very easy. So you multiply it by 2 pi, so you have 2 here, and then delta omega minus k omega naught. Okay, so therefore if you want to plot this, you will see the envelope is there because it's a sine k divided by k kind of an expression, and then at each of these locations we will locate impulses. This is particularly for t equals 41. So envelope is just there for the representation, but actual Fourier transform are these impulses that we have drawn here, this and so on. Okay, so one more example. Find the Fourier transform of sine omega naught t and cos omega naught t. Okay, so we know that sine omega naught t, the Fourier series coefficients of this signal are 1 over 2j and 1 over minus 2j, because we can write sine omega naught t as e to the power of j omega naught t minus e to the power of minus j omega naught t divided by 2j. Yeah. So therefore we know the Fourier series coefficients, so therefore we can obtain the Fourier transform in this fashion. What we do is we multiply these by 2 pi and locate impulses here at delta omega minus omega naught, and here delta omega plus omega naught, and so on. Similarly, for the cosine, the Fourier series coefficients of this signal are half and half. Therefore, the Fourier transform would be, because you have to multiply this by 2 pi and locate impulses at minus omega naught and omega naught. Okay, now let's do this example. Find the Fourier transform of the impulse train delta t minus kt. So let's see whether this is the plot of that. So for different values of k, you have to plot it. So let's take values like k equals 0. You have delta t, k equals minus 1. You have delta t plus t. For k equals minus 2, you have delta t plus 2t. For k equals 1, you have delta t minus t. For k equals 2t, and so on. You have delta t minus 2t, and therefore these are those impulses. So we know the Fourier series coefficients of those. So we can find ak by 1 over t. Ak equals 1 over t minus infinity. Sorry, integral over 1 period xt e to the power of minus j omega naught t dt, jk omega naught t dt. So therefore what have I written here? So within that interval it is delta t. So here you have k. So you put t equals 0 when you for the product of this, then you will have 1 over t. So you can see every Fourier coefficient of the periodic impulse train has the same value 1 over t. So we saw that all k you have 1 over t, 1 over t. For these values of k, 1, 2, minus 1, minus 2, for all these things value is 1 over t. So how do you obtain the Fourier transform? By multiplying each of these by 2 pi, means 1 over t multiplied by 2 pi, and locating pulses at omega minus k omega naught. Okay, so therefore you have this form. So for omega naught we have put 2 pi over t, and there you go. Thus, the Fourier transform of a periodic impulse train in the time domain with period t is a periodic impulse train in the frequency domain with the period 2 pi over t. Yeah, so that's the time domain signal, and this is the Fourier transform at these frequencies. Height is 2 pi over t. Okay, so what we did today were some examples of Fourier transform computation, and we saw once again that when the time domain signals is real and even, Fourier transform is real and even. So otherwise the Fourier transform is complex. We have to plot the magnitude and the phase if we have to plot it. Then we saw that when the time domain signal shrinks in duration, frequency domain signal expands in frequency, and vice versa. Also we saw the form of the sinc appearing, particularly for the square pulse, and later on we looked at the Fourier transform computation for periodic signals, so that we have one unified representation Fourier transform for periodic and aperiodic signals. Thank you.